This week in environmental science, we'll be studying Chapter 11, Geology, Minerals, and Mining. This lecture will help us understand Earth's internal structure and plate tectonics, rocks in the rock cycle, geologic hazards, mineral resources, mining methods, impacts of mining, reclamation and mining policy, and sustainable use of minerals. Our central case study for this chapter is mining for cell phones. If you take a look at your cell phone, you probably didn't know that it contains a non-well known metal called tantalum. Just a tiny amount, but no cell phone could operate without it. Tantalum is number 73 on the periodic table of elements. In many ways, tantalum links our glossy global high-tech economy with one of the most abused regions on Earth, the Democratic Republic of the Congo. Tantalum comes from a dull, blackish mineral called tantalite, which often occurs with a mineral called columbite. So the ore is referred to as columbite tantalite, or coltan for short. In eastern Congo, men dig craters in rainforest streambeds, panning for coltan, just like humans did in early California when they panned for gold. Unfortunately, after the 1990s, when cell phones really hit their global high, it not only led to people mining for it in the Congo, but others taking over the people who were owning the mines in a violent and brutal way. Since 1998, the war in the Democratic Republic of the Congo has killed over 5 million people. In 2001, an expert group of the UN determined that the coltan riches were fueling and financing and prolonging the war. Soldiers controlled mining operations and forced farmers and others to work while taking most of the ore and the money that comes along with it. People also entered the national parks and killed wildlife, cleared rainforest, and caused ecological havoc. And profits from the coltan sales continued to finance the war. And most of the tantalum goes to China from the Congo, where they put it into cell phones and other high-end electronics. And then we buy it here in the United States. So what is being done about it? Steps are being taken to support legitimate Congolese mines while preventing the exploitation that has been happening in the recent past. There's been efforts to make a certification system for manufacturers of electronics to also report the origin of the tantalum in their products. These opportunities and others provide an opportunity to significantly reduce trade in conflict minerals while promoting trade of minerals sourced from legitimate mines in poor nations like the Congo. Hopefully, we can provide a framework that not only satisfies the world's demand for mineral resources, but also protects the people and ecosystems that provide them. Geology is the physical basis for environmental science. It's about the Earth. And isn't environmental science also about the Earth? Making geology the basis for studying environmental science. We extract raw minerals from beneath our planet's surface, and we turn them into products that we use every day. Geology is the study of the Earth's physical features, processes, and history. A human lifetime is just a blink in the eye of geologic time. Our planet consists of many layers, and most geologic processes occur near the surface. But if we were to go down further into the earth, we'd find in the middle the core. It's a solid iron center of our earth, and there's molten iron in the outer core, meaning it's flowing and liquid-like. Outside of that area, we'd find the mantle. It's less dense than the core and has what's said to be a kind of an elastic rock area. It also contains the asthenosphere, which is very soft or melted rock. Next, we'd go further outward toward the crust, and before we would find the lithosphere, which has harder rock that also contains the mantle and the crust. The crust is a thin and brittle low-density layer of rock that you and I walk on. Over in the picture, off to the right, we can see diagrams of these. And we can also see how far we would have to travel if we were to actually go to those areas. For instance, the actual most inner part of the core is 3,950 miles away from you right now. Earth is continually being reshapen. That's called plate tectonics. It's the movement of the lithospheric plates. Heat from the inner Earth drives convection currents, and it pushes the mantle soft rock up as it warms, and then down again as it cools, just like a conveyor belt. And the moving mantle will drag the lithosphere with it. Continually, this has been pumping out new rock while dragging down old. Continents have combined and separated and recombined over millions and millions of years. The last time all of the continents were together was about 225 million years ago. We call that big supercontinent Pangaea. It was about at the time when the dinosaurs on Earth were really at their prime, and some of the biggest beasts walked the Earth, and they didn't have oceans in between to get to the different coasts. It was all connected as Pangaea. The Earth today has 15 major tectonic plates, and the movement of these plates will influence the climate and also evolution. Though keep in mind, this movement of these plates is usually very slow, maybe only a few centimeters a year. But given thousands to millions of years, it really does make a difference, and we can see how they've actually moved across the Earth's crust. There's three types of plate boundaries. There's what are called divergent plate boundaries. This is where rising magma, which is molten rock, pushes plates apart and creates new crust, as seen in the diagram to the right. There's transform plate boundaries. This is where two plates meet and they slip and grind past each other. This friction of these two plates meeting and slipping and grinding past each other is what spawns earthquakes along these strike-slip faults. A fault is a fracture in the crust. The third kind are called convergent plates, and this is where the plates collide. So, one thing that can happen when plates collide is subduction, where one plate slides beneath the other, and molten rock erupts through the surface in volcanoes, and the ocean crust slides beneath the continental crust. Two plates of continental crust collide and then lift material. And this is the type of process that has built some of Earth's features, such as the Himalaya and the Appalachian Mountains. And as we know, tectonics builds mountains. It shapes the geography of the oceans and islands and continents. It also can form large lakes. The topography created by tectonics shapes our climate as well. It alters patterns of rain and wind, currents, heating, cooling, which affect rates of weathering and erosion on Earth, and the locations of our biomes, which then affect evolution and extinction. It's all connected. The rock cycle alters rock. The rock cycle is the heating, melting, cooling, breaking, and reassembling of rocks and minerals. A rock is any solid aggregation of minerals, and a mineral is any element or inorganic compound. It has a crystal structure, and it has a specific chemical composition and distinct physical properties. Rocks help to determine soil characteristics. The type of rocks you have in an area will determine what your soil is like. It influences then what kind of plants can grow in that region's community. And it helps us appreciate the formation and conservation of soils, minerals, fossil fuels, and other natural resources. There's different types of rock. A magma is molten liquid rock, and lava is magma, which is released by a volcano. When the magma cools, that's called igneous rock. Sediments are rock particles formed by physical erosion or chemically from precipitation of substances. And sedimentary rock is formed as the sediments are pressed together and bound by dissolved materials. Compaction and transformation also then can create fossils from organisms that die and are quickly covered up after death. And then we find these fossils within the sedimentary rock. It's also nice because as these fossils are in this layer of sedimentary rock, we can date the rock and infer the age of the fossils as the same as the rock. Metamorphic rock is rock that's deep underground and subjected to great heat or pressure, which then changes its form. Some consequences of plate tectonics are geologic hazards, unfortunately, that we humans must often deal with, and these include earthquakes and volcanoes. There's a place called usually the Ring of Fire by most people, but can also be called the Circum-Pacific Belt. It's an arc of subduction zones and fault systems where most of our Earth's volcanoes and earthquakes occur. And you can see that in the chart to the right. Earthquakes then result from these movements at these plate boundaries and faults. An earthquake is a release of pressure along plate boundaries and faults. Some can do tremendous damage to life and property, especially with loose and saturated soils, and cities that are built on landfills are especially vulnerable. Buildings can be built and retrofitted to decrease damage if you know you live in an area where earthquakes often occur. Volcanoes are another thing that we humans must deal with. Volcanoes give us molten rock and hot gases and ash, and erupts through the Earth's surface, sending these things up and outward. But then they can cool and create a mountain. Lava can exit in rift valleys, ocean ridges, subduction zones, and in hotspots, which are holes in the crust. It can flow slowly or erupt very suddenly. Pyroclastic flow is the fast-moving cloud of gas, ash, and rock that can sometimes exit a volcano. It's what actually buried Pompeii in AD 79. When volcanoes erupt, the ash can block sunlight, and sulfur emissions can lead to sulfuric acid and block radiation and cool the atmosphere. Large eruptions can decrease temperatures worldwide. For instance, Mount Pinatubo in the Philippines in 1991. We can find that on the chart to the right. It lowered world temperatures almost a degree Fahrenheit. Mount Tambora's eruption caused the 1816 year without a summer and killed 70,000 people. This is an interesting chart over to the right. We can see some notable volcanic eruptions and note their magnitude, with 0 being least powerful to 8 most powerful. This interesting one is actually not too far from home here, which occurred, well, I guess quite a long time ago, 640,000 years before present, in Yellowstone in Wyoming. Here's one that occurred in Oregon about 6,800 years ago, which created Crater Lake. Here's the one at AD 79 that buried Pompeii and Herculaneum. And we've got a few in Indonesia. Here's one I remember from 1980 when Mount St. Helens erupted in Washington. And here's one from Hawaii. And then Mount Pinatubo. And this one here in Iceland, though I'm not going to try to say the name there. Landslides are another occurrence on Earth. They're a form of mass wasting. A landslide is a severe sudden mass wasting with large amounts of rocks and soil flowing downhill. Mass wasting is the downslope movement of soil and rock due to gravity. It occurs naturally, but can also unfortunately be caused by humans when we loosen soil and expose it. Mudslides are when soil, rock, and water movement are caused by saturated soil from heavy rains. And lahars are extremely dangerous mudslides caused when volcanic eruptions melt snow. In fact, the town of Oso, Washington, was buried in 2014 by a massive landslide. Tsunamis can follow earthquakes and volcanoes and landslides. A tsunami is a huge volume of water that are displaced by earthquakes, volcanoes, and landslides and can travel thousands of miles across oceans. They can not only damage our own crust on the continents, but damage coral reefs within oceans. They can also damage wetlands as well because of the saltwater contamination. Agencies and nations have increased efforts to give residents advanced warnings of these approaching tsunamis. Preserving natural vegetation like mangrove forests decreases the wave energy of tsunamis. On March 2011, an earthquake off Japan triggered a massive tsunami. The earthquake and tsunami killed 9,000 people and caused hundreds of millions of dollars in damage. Radioactive material also escaped from a nuclear power plant, so it can have even a bigger toll on us. We can worsen or lessen the impacts of natural hazards. We also face other natural hazards like floods, coastal erosion, wildfires, tornadoes, and hurricanes. And Oftentimes, people live in these susceptible areas because of overpopulation of humans. We choose to live in attractive areas as well, but unfortunately, these can be vulnerable areas, such as in mountains or off coastlines. Engineered landscapes can increase the frequency or the severity of hazards, such as damming rivers and suppressing fire and clear cutting and mining. It changes climate pattern through greenhouse gases, changes rainfall patterns, and increases drought and fire and flooding and storms. We can decrease impacts of hazards through technology, through engineering, and by making good policies that are informed by the study of geology and ecology, such as, for example, building earthquake-resistant structures can help decrease damage. We can design early warning systems so people can be warned to reduce death tolls from items like tsunamis and volcanoes. We can preserve reefs and shorelines, which can reduce the effects of tsunamis and erosion. Better forestry management and agriculture and mining, we can reduce the occurrence of landslides. And making regulations and building codes and insurance incentives can discourage development in these vulnerable areas. And mitigating climate change can also reduce natural hazards. Earth's mineral resources. Elements from minerals that we mine are everywhere in the products we use in our everyday lives. This scene in the picture is from a typical college student lounge and points out just a few of the many elements from minerals that surround us. From the silica and lithium in this gentleman's glasses to the zinc and manganese in the batteries for their radio, the tungsten in the light bulb, and of course the tantalum that we talked about earlier in this gal's cell phone. We obtain these minerals from the earth through the process of mining. Mining in the broad sense is the extraction of any non-renewable resource and can include fossil fuels, groundwater, and minerals. Mining in relation to minerals is the systematic removal of rock, soil, and other materials to remove the minerals of economic interest, the ones that we want, that we know are going to build products that can be sold. Because minerals occur in low concentrations, concentrated sources must be found before mining is begun. We use minerals extensively. In fact, it says a child born today is predicted to use 3 million pounds of minerals over his or her lifetime. We don't notice how many mined resources we use, obviously. The average American uses 37,000 pounds of new minerals and fuels every year. At this level of consumption, it shows the potential for recycling and reuse. A metal is an element that is lustrous, opaque, that means you cannot see through it, and malleable, meaning it can be formed and like pounded with a hammer and reshaped, and it can conduct heat and electricity. An ore is a mineral or grouping of minerals from which we extract metals, and metals are extracted from ores. Here's a capacitor containing tantalum, and this is what molten ore looks like. Economically valuable metals from ore include the following: copper, iron, lead, gold, aluminum, and tantalum, which is used to manufacture electronics like our cell phones. We process metals after mining the ore, because most minerals must be processed after mining. After the ore is mined, rock is crushed, and the metals are isolated by chemical and physical means. And the material is then processed to purify the metal of interest. An alloy is a metal that's mixed, melted, or fused with another metal or nonmetal substance, such as steel is an alloy of iron and carbon. Smelting is the heating of ore beyond its melting point and then combining it with other metals or chemicals. This modifies the strength and the malleability, that means flexibility, etc., of the metals. Processing minerals exerts environmental impacts, of course, and most methods are water and energy intensive, meaning we use our Earth's resources of water, energy to do these things. Chemical reactions and heating to extract the metals from the ores emits air pollution and toxic waste as well. Tailings are ore that's left over after metals have been extracted. They pollute soil and water and contain heavy metals and chemicals like cyanide, which is a poison, and sulfuric acid. Surface impoundments are stores of slurries of tailings, and accidents can release pollutants into the environment. For instance, in 2000, a breach of coal tailings impoundment near Inez, Kentucky, released over 1 billion liters. That would be 250 to 300 million gallons of coal slurry and blackening 120 kilometers or 75 miles of stream, and killed aquatic wildlife and affected drinking water supplies for many communities. We also mine nonmetallic minerals and fuels. For instance, sand and gravel provide fill and construction materials. Phosphates that come from rocks provide fertilizer for our lawns and our fields. Limestone, salt, and potash are also mined. Blood diamonds are mined and sold to fund and prolong and intensify wars in Angola and other areas. And it forces poor people to mine for labor and be exploited. And substances can be mined for fuel as well, such as uranium, which is used in nuclear power plants, coal, petroleum, natural gas, oil sands, oil shale, methane hydrate, which are not minerals, but they are organic. These items are mined as well, such as using coal for fuel. Minerals we use come from all over the world. This is an interesting chart to see where some of these things come from. For instance, gold from South Africa, tantalum here from Australia, nickel from Cuba and Australia, to name a few. Mining and its methods can definitely have their impacts. Mining does provide jobs and money for people in communities, and of course it provides the raw materials for the products that we humans know and love to use. But mining has environmental and social impacts as well, such as the removal of the large amounts of materials during mining and how it disturbs lots of land. Different mining methods are used to extract different minerals, and the method that's used depends on its economic efficiency. Strip mining. This removes layers of soil and rock to expose the resource just below the surface. We use this for coal, oil sands, sand, and gravel. Heavy machinery removes the overlying soil and rock, which is termed overburden, from the strip of land, and then the resources is extracted. Then the strip is refilled with the overburden, and the miners proceed to an adjacent strip of land and repeat the process. This does cause severe environmental impacts, such as destroying natural communities over large areas, and it triggers erosion. Acid drainage is when sulfide in newly exposed rock reacts with oxygen and rainwater and produces sulfuric acid. This sulfuric acid leaches toxic materials from the rock which then flows into streams and can have the potential to kill fish and other organisms, and pollute our groundwater, which we use for drinking and irrigation. Although acid draining is natural, mining greatly accelerates it by exposing many more new rock surfaces all at once than what would have naturally been disturbed. We've now reached our science behind the story. Can acid mine drainage reduce fracking's environmental impact? A study led by geologist Avner Vengosh of Duke University investigated whether the acid mine drainage leaking from old coal mines could be put to use to lessen the environmental impacts of the very modern process of using hydraulic fracturing or fracking to produce natural gas. Hydraulic fracturing injects water laden with drilling chemicals into layers of shale rock deep underground, fracturing the rock and releasing natural gas trapped within. Along with natural gas, fracking wells pull up wastewater called flowback fluid, made up of drilling chemicals mixed with water containing dissolved salts and toxic metals like barium and strontium, and radioactive radium isotopes from deep underground. Previous work from the team found that the standard treatment of this wastewater was only partially effective in removing its contaminants. Clearly, a more effective method of treating wastewater would be necessary to protect the water quality near fracking sites. The researchers used two types of acid mine drainage. Synthetic acid mine drainage, which is a solution mimicking natural acid mine drainage that researchers commonly use in laboratory tests, and then also acid mine drainage from the two field sites. These samples were modified on site in Pennsylvania by the addition of the mineral lime, Lime, which raises the pH and lowers the iron content of the acidic drainage, reducing its impact on waterways. Working in the laboratory at Duke University, each of these samples of acidic drainage was combined with fracking wastewater in mixtures. And the samples were shaken then for 48 hours to promote mixing, and then their concentrations of select chemical constituents were analyzed. The effectiveness of treatment varied both by type and acid mine drainage, whether it was the synthetic or the field collected type. The team found that within 10 hours, very high percentages of the barium, strontium, and sulfate, which gives acidic drainage its low pH, and radioactive radium precipitated out of solution. The process was also effective in greatly reducing the salt content of the wastewater. After these reactions, the contaminants from wastewater were concentrated in precipitate, and mostly in the form of strontium barite. Because they were not dissolved or suspended in solution, the contaminants were efficiently collected for disposal. This study demonstrated that there is potential for treating fracking wastewater with mixtures of acid mine drainage, removing some of the contaminants as precipitates, that means solids, and producing water that could be less damaging to the environment or reused in drilling applications. Although lab experiments were successful, the next step is to test the process at actual fracking sites where conditions are less controlled. In subsurface mining, miners work underground. It accesses deep pockets of a mineral through tunnels and shafts that can be up to 2.5 miles deep. And we do this to get items like zinc and lead, nickel, tin, gold, diamonds, phosphate, salt, and coal. This is the most dangerous form of mining and subjects people to dynamite blasts and the possibility of collapsed tunnels, toxic fumes, and coal dust that can affect a person's health over time, and collapse tunnels and can cause sinkholes. Open pit mining creates immense holes. Open pit mining is used with evenly distributed minerals, terrace so that workers and machines can move about. And we use this for items like copper, iron, gold, diamonds, and coal. Quarries are open pits for clay, gravel, sand, stone, including limestone, granite, marble, and slate. Huge amounts of rocks are removed to get small amounts of minerals. This has an impact on our environment, which includes habitat loss. It has aesthetic degradation, meaning it doesn't leave the landscape looking very good after this process is done, and can include acid drainage, leaving abandoned pits full of water that is unhealthy. Here's the world's largest open pit mine in Utah. It's 2.5 miles across. And almost 500,000 tons of ore and rock are removed each day. It is absolutely immense. Placer mining uses running water. Placer mining using running water has miners sifting through material in riverbeds. And we know in the U.S. we've used this in the past for mining of gold and gems. It occurs that the debris washes into the streams and then they become uninhabitable for wildlife. And this disturbs our stream banks and causes erosion and can harm plant communities. Mountaintop removal reshapes ridges and can fill valleys. Mountaintop removal mining is when the entire mountaintops are blasted off. Valley filling is the dumping of rock and debris then into the valleys of the mountain. We've done this for coal in the Appalachian Mountains in the eastern U.S. It degrades and destroys vast areas, pollutes streams, deforests areas, and causes erosion, mudslides, flash floods, and biodiversity loss. And mine blasting cracks the foundations and walls and causes floods and rock slides that can affect our properties. Coal dust and contaminated water can cause illness in humans, which can also lead to other types of diseases like lung cancer and heart and kidney disease, pulmonary disorders, hypertension, that's high blood pressure, and death. The poor people of the Appalachia suffer while other people benefit from the coal-produced electricity. Critics argue that valley filling violates the Clean Water Act. In 2010, the EPA introduced rules to limit this damage. Solution mining dissolves resources and extracts resources in place. Solution mining, also called in situ recovery, this is when resources in a deep deposit are dissolved in a liquid and then sucked out. Water, acid, and other liquids are then injected into the holes, and it's used for getting items like salt, lithium, boron, bromine, magnesium, potash, copper, and uranium. This one has less environmental impact than the other methods, because less area is disturbed. But acids and heavy metals and uranium could accidentally leak out and contaminate groundwater and other areas of the environment. Some mining even occurs in the ocean. We can extract minerals like magnesium from seawater. Minerals can also be dredged up from the ocean floor. Manganese nodules, which are small ball-shaped ores, are scattered across the ocean floor. And these reserves may exceed all terrestrial reserves. Logistical difficulties in mining have kept extractions limited so far. It's difficult to mine things that are so deep underwater. Restoring helps reclaim mine sites. Governments in developed countries require companies to reclaim or restore surface mined sites. This is called reclamation. It aims to bring a site to a condition similar to its pre-mining condition. This includes removing structures and replacing the overburden that had been removed, and then replanting vegetation over the top of that. The U.S. Surface Mining Control and Reclamation Act of 1977 mandates this restoration. Companies must post bonds to cover restoration costs. Even on restored sites, though, impacts can still be severe and long-lasting. Complex communities that once lived in a mined area could be simplified. Essential life there could be lost, especially if the correct grasses and plants and things are not replaced properly. Essential symbioses, which are relationships between different organisms, could be eliminated and possibly not restored, because it's hard to know after we remove things from an area exactly what was all there. It's easy to see, yes, that the buffalo were there, but what were some of the smaller organisms or the microorganisms that occupied that habitat? Those things may not be completely replaced. Water can be also reclaimed and moderate the pH and remove heavy metals. An 1872 law still guides U.S. mining policy. The General Mining Act of 1872 encourages metal and mineral mining on federal land. Any citizen or company can stake a claim on or buy for $5 an acre any public land open to mining. The public gets no payment for any minerals found there. Supporters say it encourages a domestic industry that's risky and requires investment to locate vital resources. Critics say that it gives valuable public land basically free to private interests. People have developed the land for uses, for instance for condominiums that have nothing to do with mining, and efforts to amend this act have failed in Congress. Minerals are non-renewable and resources are limited in supply. We must remember this. Many minerals are rare and could become unavailable. Once known reserves are mined and minerals then will be gone. For example, indium, which is used in LCD screens, might last for only 30 more years, and gallium, which is used for solar power, and platinum for fuel cells are also scarce. Estimating how long a reserve will last is hard, it's difficult. New discoveries and technologies, consumption patterns, and recycling affect mineral supplies, and as we know, as a human society, often change. As minerals become scarcer, then it causes prices to go up, which has an effect on the consumer. Here's a chart with some thoughts on minerals that are non-renewable and how long they'll be available. The major reasons why non-renewable resource availability estimates may increase or decrease over time could be because of the discovery of new resources, because of new extraction technologies, changing social and technological dynamics, changing of consumption patterns, and recycling. We can use minerals sustainably. Recycling minerals addresses the finite supplies on Earth and the environmental damage on Earth. 35% of metals are currently recycled from the U.S. from solid waste, and 33% of our copper comes from recycled sources. Recycling decreases energy use and also helps to lower greenhouse gas emissions. Electronic waste, which is nicknamed e-waste, from computers, printers, cell phones, and etc., those things are rapidly rising. Recycling helps keep these hazardous materials out of landfills while conserving mineral resources. Cell phones, we need to learn, can be refurbished and then resold in developing countries. Or their parts can be dismantled and refurbished. Today, only 10% of cell phones are actually recycled. Recycling reduces the demand for virgin ores and reduces pressure on Earth's ecosystems. In conclusion, geologic processes shape Earth's terrain and form the foundation for living systems. We depend on minerals and metals to make our products. Mineral resources are mined by various methods and contribute to our material wealth, but cause extensive environmental damage, habitat loss, acid drainage, and other. Restoration and regulations help to minimize the environmental and social impacts of mining, and recycling and sustainable use prolong mineral resources.